Hello students, in this video we'll discuss complex differentiability Cauchy-Riemann equation. Class. Be evaluated from C in open set omega and C in open. Hold the needle here. We said that F is differentiable z equals z0 if the following limit exists. If the limit as h approaches 0, h a complex number, so this is a limit as h goes to 0 when h is a complex number, so h can be any complex number you want, which means that this is a two-dimensional limit, not a one-dimensional limit, okay? Of what? The limit, which is 0 for complex values h, of f of z0 plus h minus f of z0 over h. That looks like our ordinary difference quotient. And when this limit exists, say that is equal to f prime of z0. Easy enough. Let's see some examples of this, okay? Here's the first example. F of z, it's z squared. Hamel's residual error is everywhere differentiable. Okay, the proof of this is easy, right? Standard calculus proof. So I want to prove it as h complex, h goes to 0, complex, very important. Then I can have a z plus h squared minus z squared over h. Right. H is complex again. According to the limits, h goes to 0. Well, that's going to be a z squared plus 2zh plus h squared minus z squared over h. It's canceled out. One of the h just cancels out, right? As long as h is not 0. And so this is equal to the limits as h goes to 0. That cancels with that and that cancel. And so now I just have of 2z plus h. That's an easy limit, that's just 2z. That's what you expect, right? You expect a derivative of z squared just to be 2z. Now let me show you a slightly different situation where not every function of mapping the complex numbers to complex numbers is going to be differentiable, right? In particular, functions who involve z bar will not be differentiable according to this sense. Well, let's see why. Okay, so here's another example. Let's look at f of z, which is mod z, is not differentiable. Anywhere. Let's prove it. You might say, well, that seems sort of strange, right? You have the limit as h goes to 0 of z plus h complex conjugate, that's the function, minus z complex conjugate, all divided by h. Well, this is just the limit as h goes to 0 of h bar over h, which of course is just going to be what? The limit as h goes to 0, the real part of h minus I, the imaginary part of h, over the real part of h plus I, the imaginary part of h, right? Now, what happened along the real part of h is equal to 0. That's a fancy way of saying along the imaginary axis. Limit as h approaches 0 of h bar over 8. Well, when 0, I'm just going to get a I imaginary part of h, I imaginary part of h with a negative sign, that's achieving -1, right? Along the trajectory, imaginary part of h is equal to 0. That's, of course, just the real axis. Yes. What? We're going to have the limit as h goes to 0 of h bar over h is equal to what? Well, now in imaginary part 0, you get real part over real part is equal to 1. So no matter what point z is, so numbers? Well, this limit does not exist, so hence lim h goes to 0, complex h bar over h. Now you can see if h is real, this limit exists, right? If h were real, then I'd be in the situation of a function of a real variable. Now we're only focusing on complex differentiable functions, right? This is going to be equal to what? This limit will not exist. Does not exist. Okay? In other words, we have this dichotomy that we're seeing. If there's any z-bar dependence, you're going to be not differentiable. If there's no z-bar dependence and only z dependence, assuming the function is fairly regular, then you're going to have complex differentiability. Okay? And so here's a definition. So we say, definition, say that a function is holomorphic on omega if its derivative exists for every point. If f prime of z exists for all z in omega. Okay? Now, in particular, the question, so this leads us to a natural question, right? So in other words, what do we know? I know that f has real and imaginary parts. So here's a question for us. So our question is the following. So question, what conditions on f equals u plus iv will guarantee u and v will guarantee that f is holomorphic. And with these equations, we're going to see these in the next video, these are called the Cauchy-Riemann equations. Okay, so Cauchy-Riemann will need to be satisfied in order for us to prove that a function is complex differentiable or holomorphic, right? So, and of course, these Cauchy-Riemann equations actually generate a lot of regularity. So we're going to see how these Cauchy-Riemann equations are an automatic regularizer. In other words, once you have some derivatives, it will provide you with more derivatives for free by virtue of something known as elliptic regularity, which is a vestige of some partial differential equations and some of the theory of PDE, which we'll discuss in a further video. Thank you very much.